Number one. Okay, you have a skier that starts at rest at the top of a hill. I already want to draw a picture. I always start things by drawing a picture if I can. So we got our hill, and we've got our skier, and we know that the skier's at rest, so we know that the velocity up here at the top is 0. Just drawing out all the information. And then is traveling at 15.5 meters per second at the bottom. So I guess the skier has skied down the hill and is now moving downward down here. Here's our skier. And the velocity, at least the magnitude of it, is going to be 15.5 meters per second. And what do we need to do? We need to calculate the work. Okay, good. There's a concept right there that I've seen before. Work done by gravity. Okay, gravity, that's something I care about. By kinetic friction and by air drag. Okay, so I know I'm going to need to use work because that's what we have to calculate. And gravity, we're usually talking about the force of gravity. And then kinetic friction, air drag, these are all forces. So I need to connect work to these forces. So the first thing I would do is think, okay, what's the connection between work and force? Well, one that I can think of right away is a work is equal to the change in position vector. That's how far the skier moved. That's basically this vector here, which we were not given, but we would need it if we wanted to solve this problem, dotted into the force. So any force, the work done by any force is going to be given by this equation. Now, so let's just start with gravity. What if we wanted to find the work from gravity? So the work from gravity, well, we would just have to say, okay, here's the force of gravity. It's just mg downward. And so we know both the force vector is this downward force, and we know this change in r vector is this vector here. And let's say that the angle between them, say that angle is theta. So that means that the dot product is going to be just the magnitude, how far the guy went down the hill, times magnitude mg times cosine of theta. Okay, what about the work done by kinetic friction? Kinetic friction. Well, we could do it the same way. We could just do it like this, dotted into now the force of kinetic friction. And so to find the kinetic friction, we would need to know that the kinetic friction is equal to mu times the normal force. So we need to know mu, and we need to know the normal force. And so if we knew the mass, and we knew the angle of the slope here, we know this angle down here, which is called that phi, then we could figure out what the force of kinetic friction was. We could find this out. And then the work done by air drag, so work done by drag, and then this one, you'd say maybe you want to do it again like this, times the force of drag. But the force of drag usually depends on velocity. It's not a constant force. So how would you do this if you couldn't use this equation for the work from drag? Well, let you think about that for a second. Okay, so the total change in energy is equal to the change in kinetic plus the change in potential plus the change in the internal energy. And so basically, since we know that we know the change in kinetic here, that's just since we know the velocity, we can just use 1/2 mv squared to get that, because we went from 0 to 1/2 mv squared, where v is going to be this here. And we know the change in potential energy also, because it's just the change in height, so that would be, I guess it would be delta r vector magnitude, but we're just worried about the height. That was this whole vector, but we're worried about just the height, so that would be times sine of this thing that I called phi, and then plus the change in the internal energy, and that's equal to the change in the energy total. And then now all we have to do, so now we just need to solve this. And oh, right, so don't forget that the change in the total energy, we're talking about the total energy of this entire system. And so the change in the total energy of the system is just 0. So now we know that 0 equals, well, let me just copy this. So 0 just equals that. And so we really only have, well, this one unknown, the change in internal energy, and the change in internal energy is going to be the work done by the non-conservative forces, and the work done by non-conservative forces is equal to the work done by kinetic friction plus the work done by drag. Wow, this one's kind of long. And so, since we know, we calculated sort of the work done by the kinetic friction here, we finally can take this whole thing, let's copy it again, and then instead of the internal energy, we know that that's equal to W kinetic plus work from drag, and then we have expressions for everything here, and the only thing we don't know is the work from drag, and we can solve for that. Number 2. A rubber bullet strikes your head, oh no, at 100 meters per second and bounces straight back at 100 meters per second. The time of impact, it is 0.03 milliseconds. Will the bullet fracture your skull? Okay, so here's your precious head. Let's draw a picture. And you have a bullet coming in at 100 meters per second, and then it bounces off at 100 meters per second in the opposite direction. Now, it's saying, will the bullet fracture your skull? What's that really asking? Well, if your skull will be fractured if it's something presses too hard on it. And by press, I mean a force. So the question is, what's the force on your skull? So we need to find a force. Force. Okay, well, we know that average force for a really quick impact like this is equal to the change in momentum over the change in time. And we don't know the mass of the bullet, but if we did, then we could write this as the mass times the change in velocity of the bullet times the change in time. And so this is just mass times, well, the change in velocity is going to the left at 100 and then to the right at 100, so the change is actually 2 times 100. It's just because this could be like negative, like minus, positive 100 meters per second, so this is going to be something like 200, it might be negative, but meters per second over, and then the time is 0. Okay, it's milli, so I've got to add 3 zeros. 1, 2, 3, 3 seconds. And that would be the force. And if we had the mass, then we could calculate a number here. And then if we also knew how much force it would take to fracture a skull, we could compare this to that. And if this number were bigger than the force your skull could withstand, then your head would be fractured, and that would be sad. Okay, let's do number 3. So, Your heart pumps about 5 liters of blood per minute through your aorta, which has a radius of 0.9 centimeters. So, as always, draw a picture. Here is an aorta, and it has a radius of 0.009 meters. And the flow is 5 liters per minute. And the question is the flow in the aorta laminar or turbulent? Well, whenever you want to know if something's laminar or turbulent, use a Reynolds number. Reynolds number, if it's low, that means it's going to be laminar flow. So Reynolds low is laminar. And a high Reynolds number, much greater than 1, is going to be turbulent flow. And so our equation for Reynolds number is the density of, here it would be blood, times the velocity of it, times some length scale involved, and that'll be the radius of the aorta here, divided by the viscosity. And so the things that we don't know here, I guess we would be given, if this were a problem on the exam, the density of blood and the viscosity of blood. And we're given L. We know that L is 0.009 meters. And the velocity, we don't quite know yet, because we do know this is basically the flow rate, 5 liters per minute. So we can convert 5 liters per minute into, we want to get it into SI units. So I believe, I'll let you do this, but I believe this goes to 8.3 times 10 to the minus 5 meters cubed per second. And don't forget that, so this flow rate is, right, this is Q. And don't forget that Q is also equal to the area times the velocity. And here we know that the area is going to be pi 0.009 meters squared. And we know that this is the flow rate. So Q is the flow rate. And from these two, we can find what the velocity is. Just rearrange that equation to get V equals Q over A. And then with this, our radius as L and the density and viscosity of blood, we can figure out whether or not the Reynolds number is small, laminar, or big, turbulent. Okay, so next it asks, the capillaries in your body have a radius of 4 microns, or 4 micrometers. And blood flows through the capillaries at a speed of 5 times 10 to the minus 4th meters per second. How many capillaries do you have? Okay, so basically, the picture that I would draw here is I'd say, okay, well we have, what's going on here is we have our aorta, and then something happened, it goes through your body, and then eventually it branches into all these little capillary tubes. So there's way more than I'm drawing here, but you kind of get the idea that the flow goes into the capillary tubes. And the flow in one of these little capillary tubes is going to be outward at 5 times 10 to the minus 4th meters per second, and the radius of one of these capillary tubes is going to be 4 microns, which is 4 times 10 to the minus 6 meters. So the amount of fluid that goes in the aorta here, that's going in here, is going to have to be the same amount that's going through all the capillary tubes. So that basically means that the flow Q in the aorta is equal to the flow Q in all capillaries. So basically what that means is that the area of the aorta times the velocity of the blood going through the aorta is going to equal the number of all the capillaries, times the area of one capillary times the velocity of blood through the capillary. So what we can do is since we know the problem gave us the velocity in the capillary, it essentially gave us the area because it gave us the radius of a capillary. We know the area of the aorta because we know the radius of the aorta. And so we can solve for, and we also calculated the velocity in the previous part of this problem. So we know everything here except for the number of capillaries. So we can just solve number of capillaries is equal to area of the aorta, velocity of the aorta, let's make this a little a, divided by area of the capillary, V capillary. Okay, number 4. The surface tension in the alveoli is about 3 millinewtons per meter. Okay, so first let's draw this. So an alveolus is some hollow cavity in the lung, so it's something like some little bubble thing. Alveolus. So alveolus, singular for alveoli. And then there's some pressure in here. This is a bubble. There's a pressure inside and then a pressure outside. Whenever I have a bubble, I just keep that in mind. So okay, if a pressure difference of 30 millimeters of mercury is required to inflate the alveolus, what is the radius of the alveolus? Okay, so that means that the pressure difference, P in minus P out, is equal to 30 millimeters of mercury, or if you want to put this in SI units, which is usually a pretty good idea, you just multiply by 500 pascals divided by 760 millimeters of mercury, and you'll get what this change in pressure is in SI units. And then this is just clear, to find the radius of the bubble, this is a clear use of our change in pressure is equal to 2 gamma over R. This is basically the equation that says the pressure inside minus the pressure outside a bubble is equal to 2 times the surface tension, which we know here is 0.003 newtons per meter, divided by the radius, which we're trying to find, and we know everything else in this problem, so we can find the radius. The equation is just going to be R equals 2 times 0.003 newtons over meters times our change in pressure, which you can calculate by looking at this. Number 5, a softball pitcher with an 80 centimeter long arm accelerates the softball from rest to a speed of 32 meters per second through 500 degrees of rotation. What's the angular acceleration required? Okay, as always, got to draw the picture. So something like a hand, more like a hook there, but anyway, it goes around 500 degrees. It's our theta. And we know that the length of this is 0.8 meters. And what else do we know? We know that, we have the word rest here, so that means that V naught is equal to 0. And eventually we get to 32 meters per second, so that's V final is equal to 32 meters per second. And we're looking for angular acceleration, so we're looking for alpha. So we need something to connect theta, alpha, velocities. But we don't have time anywhere in this. It's not asking us for how long this takes. So since it's angular, we'll probably have to use one of these angular kinematic equations, and we'll probably use one that doesn't involve time. So if you look at your cheat sheet, hopefully you have this one. omega final squared equals omega naught squared plus 2 alpha, which I think we're assuming is constant here. That's something that wasn't said, but safe to assume. Otherwise, we couldn't solve this. So, times the change in the angle. And so here, don't forget that we were given these velocities. Now we're looking for the angular velocities, but don't forget that omega is equal to v over r. Well, initially we have no v, so that means no omega. So this initially is 0. So then we can use this equation for the final velocity, and we could rewrite this equation as v final over 0.8 meters of v final. Let's just put in the number. V final is 32 meters per second squared is equal to 2 alpha and then delta theta, which we know is going to be 500 degrees, or we could multiply this by 180, or I mean rather pi over 180 degrees, have the degrees cancel out, and we'll get a delta theta in radians. And so now this equation will tell us everything we need to know to solve for alpha. Number 6. You fall from a height h and you land stiff-legged so that you come to a stop over a duration of 5 milliseconds. As always, I really enjoy drawing a picture, so let's draw a picture here. And then what's happening is you're falling a height h, and then after a height h, so basically this is your center of mass here. Now down here your center of mass is here. Okay, then you land stiff-legged, and then you come to a stop over a duration of 5 milliseconds. So that's a new, something else is happening after you fall. Basically, you I guess your center of mass is, if you're coming to a stop, that means you're still moving. So you land and then you fall a little bit more, and then you come to a stop, and the duration for that is 0.005 seconds. And at the end, let's call the final velocity when you're at rest, call this like let's call that v2 equals 0. And then you have v1, which we don't know, which is right when you first hit the ground before coming to rest. And then you have, say you have a v naught up here is equal to 0. So those are all your speeds. And then what's the question looking for? Right. So it's asking for the maximum height from which you can fall without breaking your legs. So okay, we're missing some information because I know nothing about what it takes to break a leg. But when you're talking about breaking something, you're usually talking about pushing on the legs, and that pushing is usually a force. So you can imagine that there is some force of breaking, some maximum force that would cause your legs to break. Okay, but this problem is asking about height. So how can we get this in terms of height, or, maybe a velocity or something like that? Well, the best thing to do is to write down what we know about forces. So what is force? Force is mass times acceleration. Okay, so that's good. There's probably an acceleration of braking, like the highest acceleration you could have right on the edge of your legs braking. So that's good, but we still don't have a height. So okay, let's keep going and write this as mass times, so what is acceleration? Acceleration is, well, the average acceleration is the change in velocity over the change in time. Okay, that's good, but what velocities and what times are we talking about? Well, if we're talking about the acceleration or the force while we're landing, then the velocities we're talking about is the change is going to be v2 minus v1. v2 is 0, so here I'll just rewrite this for this duration right here. So we have our m times, and then our change in v is going to be final minus initial. v2 is 0, so this is going to be minus v1. And then over the change in time, and we know that duration is 0.005 seconds. Okay, so now we have at least a velocity in here, and so we have v1. Okay, that's good because v1's in the picture, so we're getting closer. But how do we figure out how we could possibly relate v1 to the height? Well, when you're trying to relate velocities and accelerations and lengths, always look for your kinematic equations that you probably have on your cheat sheet, and you probably remember this one. V final squared equals V initial squared plus 2g times h, or delta y, but I'm calling it h here. And so where should we apply this? Well, the height that we want to talk about is this height. So that means we have, for this falling, we have a v1 is our final, so this becomes v1 squared. Our v initial is 0, so that's 0 squared plus 2gh. Or that goes to v1 is equal to the square root of 2gh. Or we could write it as h is equal to v1 squared over 2g. This is actually what we want, because we're looking for h. So okay, we're looking for h, and then we probably want to write it in terms of the force of braking and the duration. So we can take this whole thing and write it, just rewrite it as, just take this part here and this part here, and write v1 is equal to the force of braking times 0.005 seconds over the mass, and then plug this into here, and that will give us that h is equal to, put our v1 in, force of braking times 0.005 seconds over m divided by 2g. And so this is going to be the height. For this one, check out the video that was done early in the semester here. Okay, so 8. A kangaroo's Achilles tendon can be treated as a cylinder of a length L, radius R. If the Young's modulus of the tendon is 1.5 times 10 to the 9th pascals, how much energy is stored in the tendon if it's stretched by a distance d? So let's draw a little picture. So we have a cylinder. This is the tendon, and it has a radius r, and it has a length L, and then it gets stretched a little bit like this, and then it gets stretched a distance d. So whenever you have something with Young's modulus, you have a material that's pretty much acting like a spring, where the force is equal to the cross-sectional area. You should have this equation on your cheat sheet, by the way, times your Young's modulus divided by the rest length of the material, and then times the change in the material. For us, this rest length is L, and this is D. Here is our Young's modulus, and the cross-sectional area is pi r squared. So that's fine. We treat it like a spring, kind of like this, but we're looking for energy, right? And if it acts like a spring, then the energy in a spring, you got to remember, is U equals 1/2 kx squared. Where x, remember, is the displacement, or the stretching of the spring, and here for a material, our x is going to be d, and our k, if we look at our force equation for the material analogously to a spring, then this thing in parentheses, this is similar to our k. So we can write this whole thing as, for a material, the energy stored is going to be 1/2 times AY over L, and then this is d squared. And so it's just a simple plug and chug here. Number 9. Calculate the mass of ice on which a 500 kilogram polar bear could just barely float. Okay, what is this question actually asking? Well, it's saying you must have some sort of polar bear, which I'm going to draw as a block, and it's sitting on ice, which I'm going to draw as another block, and the polar bear is just barely floating, so that means there's some water somewhere, but it's not quite at the polar bear's level, but it's almost there, so that means that it's probably like somewhere just like right at the top of the surface of the ice. Sorry, this should be at the same level as the ice. And so, what are we looking for? We're trying to calculate the mass of the ice, right? So how should we do that? How do we calculate the mass here? Well, this problem involves ice in water, so there's going to be a force, a buoyant force pushing up. And we have also the polar bear is 500 kilograms. So we have some masses, we have some buoyant force. So if we have forces, if we're looking for masses, I say let's do a free body diagram to put all those things together. So okay, let's do it with the ice. So what forces are on the ice? Well, there's a buoyant force, then there's also mass of ice times gravity, and then also the polar bear is sitting on the ice, so it's pushing down with its force on the ice, so that means we're going to have a downward force of m polar bear times gravity, and the ice is standing still. So basically what this means is our equation for this free body diagram is m ay, acceleration in the y direction, which it's not moving, is equal to 0, is equal to our buoyant force upward minus m ice times gravity minus m polar bear gravity. And so we could rewrite this as, so remember that the buoyant force is equal to rho of water times volume displaced times gravity. So we can plug that into this equation here, put this up in there, and what we'll get is, I'll rearrange this a little bit, so we have rho water, V, remember that's V displaced, times G is equal to G m ice plus m polar bear, and then we have G's everywhere. We can cancel out our G's, and then now we're looking for the mass of the ice, but we would probably be given the density of the water and the volume of the water. Would we be given that? Or rather, would we have to be given that? Well, it seems like we would have to know something about the volume here. But this is the equation that you would use, and hopefully that is helpful. Okay, so 10. Blood flows rapidly through a large artery. Large meaning that it's probably not viscous. Part of the artery becomes obstructed, and the obstructed region has a radius 1/3 of that of the unobstructed region. Okay, so before they ask the question, I'm going to draw a picture. So we have the large region, obstructed region, large region, obstructed, large region. I'm sorry, horrible drawing there. let's say that the radius is r over here, and then in the obstructed region, the radius is r over 3, as it tells us. Now the question is, how much does the pressure drop in the obstructed region? Okay, so we have flowing fluid, and when it's a large artery, there isn't viscosity or anything. There's really one equation that should come to mind in a situation like this, and that's Bernoulli. Bernoulli. So what is Bernoulli's equation? Well, it is at one point the pressure plus rho g height at that region where that pressure is P1. So let's call this area, let's call this 1 here and call this 2 right here. So it's going to be plus 1/2 rho v1 squared, and then that's just equal to the same expression, but just at point 2, rho gh2 plus 1/2 rho, where rho is, remember, just the density of blood, v2 squared. Okay, so you probably know where to go from here, but you actually are going to have to use the continuity equation, so I'll go a little further. So looking at this equation, let's keep in mind that the height at these two places is about the same, so these two terms are the same and we can cancel them out. Now let's rearrange this. Let's say, rewrite it as P1 minus P2 is equal to 1/2 rho v2 squared minus v1 squared. Okay, so the pressure drop is this. P1 minus 2 is the pressure drop. That's what we're looking for, and that's equal to the right-hand side here. So let's look at the right-hand side a little bit harder. So we have velocity at 2, velocity at 1, but can we relate those? Maybe simplify this a bit. If we knew the velocity at one point, I think we could actually solve this. So what I mean is that the continuity equation allows us to relate v1 and v2, because continuity is that the flow rate equals a constant, or rather, at any point in a tube, A1 V1 is going to equal A2 V2. And the area for both of these can be written as pi r squared. So we have pi, in this one we have r squared V1 equal to pi r over 3 squared V2. And then this is going to give us the relation that V2 is equal to 9 V1. And so what we can do is we can put this into our equation here, and we can get, oh, sorry about that. We can get that this equals 1/2 rho V1 squared, and then this is going to be 9 squared minus 1 squared equal to 40 rho v1 squared. And if we know the velocity at 1, then we could actually figure out the pressure drop. 11. Kinesin can exert a maximum force of about 5 piconewtons, or 5 times 10 to the minus 9th newtons. What is the largest vesicle that the kinesin can carry at a speed of 0.8 millimeters per second? So basically what this is saying is you have some spherical vesicle thing, and then you have a kinesin, and it can pull with 5 times 10 to the minus 9 newtons. And so, and it's going, and it wants to pull this vesicle at 0.0008 meters per second. And so it's probably moving along some little tube there. And so if it's going to move it at a constant velocity, what that means is that the forces on this vesicle are going to be equal to 0 because it's a constant velocity, which means no acceleration. So if there are no forces on the vesicle, that means that we have to have this forward force of the kinesin pulling on the vesicle equal to some backward force, and this is probably, inside some fluid, so there's going to be a resistant drag force. So there's going to be an F drag. So basically what we need is F drag is equal to 5 times 10 to the minus 9 newtons. But we're looking for the largest vesicle, so we're looking for a radius. So remember that our drag force is going to be 6 pi viscosity times RV is equal to 5 times 10 to the minus 9 newtons. That is, of course, viscous drag, because we're in some sort of viscous fluid. For small things in fluids, you usually have some viscous drag. And so we can figure out the size by figuring out what R is. We're given V in the problem. We would be given whatever the viscosity of the fluid is, and so we know everything to figure out what R is. Okay, a flea jumps by storing energy in an elastic protein known as resilin. It can stretch the resilin 1.5 times its usual length. What is the mass of resilin required to jump 15 centimeters in the air? Okay, so mass of resilin, I think this is not the right question. Sorry if this is a confusing one, but I think what this question is really trying to get at is conservation of energy. So U spring is going to go into U gravitational, and so that just means that we'll have 1/2 k x squared equals to mgh, where this is going to be our 15 centimeters. We know g, m is the from the flea's mass, and then x is going to be this. So we're stretching 1.5 times the usual length, so that would be, so x is going to be the rest length, which we're also not given, over 2. This is going to be squared, x squared, and then k we're also not given. And then you would just solve for maybe the mass of the flea, or the height, or I guess we're given the height, but you could, if you were given everything on the left, you could be looking for the mass of the flea. But we weren't given enough here, so I hope this at least gets you thinking about conservation of energy in spring and gravity. A monkey swings from a vine length L, starting at rest at an angle from the vertical. How fast is the monkey going at the bottom of the motion? So what's the picture? The picture is you have a vertical, you have a monkey swinging on a vine, and it's at an angle theta from the vertical. And then when the monkey is down here swinging, what is our v equal to? And we know that's starting at rest, so we know v equals 0 up here. Well, we know we're going from up here to down here, so we've changed height. So we've changed some height about this much height. So that means that we had some gravitational potential that went into kinetic energy. So this is just a simple mgh equals 1/2 mv squared problem. And that's all you do, you just solve for v. But you might also ask, well, what's h? And here you have to do a little geometry. You've had a lot of practice with this, but I'll just do it quickly. So to find out what h is basically about this length here. It's from, the height, the center of mass of the monkey to, the center of the mass of the monkey, which is about the bottom of the row. You can approximate it. So this length is going to be the full length minus this right here. And this right here is equal to L cosine theta, just by using this triangle. And the full length is L, so h is going to equal the full length L minus this part right here, which is L cosine theta. So h is equal to L1 minus cosine theta. 16. You fall from an airplane and land in deep snow, forming a crater of 1 meter deep. What is the average force exerted on you by the snow during the landing? Okay, so basically our picture here is you fall 1 meter. You're up here, you go down here. And so you want to know what the force is. So let's just write F, and then remember that F is equal to ma, because we must be decelerating when we fall into the snow. So how can we do this? Well, it doesn't seem like we have enough information, but we do know that the velocity down here when you land is v equals 0, and you could imagine maybe we'd have a vi, some initial velocity at the top. And so then what we could do is we could use the initial and final velocities and our handy-dandy equation, kinematic equation, of v final squared is equal to v initial squared plus 2a change in our position. And we know that finally we have 0, because that's this, and then initially we have some velocity which we don't know, and then we know that we have x is equal to 1 meter, and then we can solve this and say a is equal to minus vi squared over 2 times 1 meter, and that gives us a, and then we could plug a into here to find what the force is. But we don't really have enough information. We don't really know what the initial velocity is. 17. A dolphin swims through the water at 10 meters per second. What is the power produced by the dolphin? Okay, so let's draw our picture. Here's the surface of the water. Here's our dolphin. A little bit of an underbite. And so, it's going at 10 meters per second. So how would you do this? I don't immediately know, so let's just write some equations for power. We're looking for power. So it equals the work over time, or it could equal force times velocity. That's what I have on my cheat sheet. So we have a velocity here, so maybe this one is appropriate, but is there a force that the dolphin is using? So this is the force would be applied by the dolphin times its velocity. Well, we're moving at a constant velocity at 10 meters per second, so there's no net forces on the dolphin. So if it's applying a force forward, for there to be no net forces on the dolphin, so if the dolphin's applying a force forward, there must be a force backward, and we're in water, so and it's probably not a viscous fluid, so the only force backward that it would be counteracting would be the force of drag from the pressure drag. And so if the dolphin's exactly counteracting that drag, we can figure out the magnitude of the dolphin's force by figuring out the drag force, and the force from pressure drag is equal to 1/2 the density of water, the cross-sectional area of the dolphin, some constant called c, and this is just depends on what object you have, basically what the dolphin's shape is, and times velocity squared. So the dolphin is going to also have the same magnitude of force, just in the forward direction, so this is also equal to the magnitude of F dolphin. And so to find the power, all you have to do is multiply this times velocity. So power is equal to 1/2 rho AC V squared times V, and we don't have enough information here because we don't have the cross-sectional area of the dolphin, we don't have the constant, but that's the equation that you would use. Okay, so the question is asking, the gauge pressure in the aorta is 100 millimeters of mercury. If you punctured a small hole in the aorta during surgery, which is kind of dark, and the blood squirts straight up, how high will it go? So we have our aorta here. There's a punctured hole in it. There's some blood flowing through here, and through the hole there's some blood that squirts up, and we want to know how high does it go. So if you're given some pressure and you're looking for some height, h, then what equation do you think of? I think of Bernoulli immediately because it has pressure and heights in it. And so remember that Bernoulli says that the quantity of pressure plus rho gh plus 1/2 rho v squared is always constant. So this quantity at one point is equal to this quantity at another point. So I'm going to make this 0.2 and this down here 0.1, and then just use this equation and see if that works. So before doing that, let's convert this pressure in millimeters of mercury to pascals. So that's 100 millimeters of mercury times 101,500 pascals over 760 millimeters of mercury. And so cancel out the millimeters of mercury, and we get this is about 13,000 pascals. So okay, let's write for situation 1 this quantity. So we have 13,000 pascals plus, this is the density of blood, which I don't know offhand, so I'll just write it as rho, times g, 9.8 meters per second, times I'll set the the 0 level for the height to be here, so the height here is actually 0, so this whole thing goes to 0 because this is at 0.1, plus 1/2 rho v squared. Now we'd have to be told what the velocity of the fluid is in the tube, but here I'm going to say that the blood isn't really moving. I don't think it moves very fast in the aorta. Not sure about that, but I'm going to approximate that to 0. And then this is going to equal the pressure up here outside at 2, which we know is going to be 1 atmosphere. But our 1 atmosphere we should probably put in pascals, because we have it in pascals over on the left. So, right, this is about 10,000, 10 times, or let's just call it, approximate it to 10 to the 5th pascals. And that is plus rho g. Now, this is the height that we're looking for. And then plus 1/2 rho v squared. But up at the top where it's stopped, and now it's going to go back down all the way up to the top, v is 0, so this goes to 0. And then we have everything we need to calculate how high the to calculate h here, because we have the density of blood, we have g, and we have the pressures. Okay, 19. Your bicep muscle can exert a force of F max. What is the maximum weight you can hold in your outstretched hand? Well, okay, let's draw a picture. So you have the bone for your arm, and then you have your bone for your forearm. You've got a bicep connecting, I guess, to your forearm here, because it's holding up your forearm, and then your hand is holding some weight. And so the question's asking how much weight, basically how much mg, can your bicep support? So to me, it looks like the question's asking, how much weight can you have in your hand before your forearm starts rotating and your bicep can't keep this from rotating, and it will rotate around your elbow here. So what that means to me is that we're going to have sum of torques is equal to 0, where you'll have one of your torques is going to be the torque from the weight, and then the counteracting torque is going to be plus the torque of your bicep. And then also there will be a torque from your elbow, but if we put the pivot at the elbow, then we won't have to worry about it. So now let's think about the signs from both of these torques. So the weight is going to make looks like a clockwise turn, so this is going to be so let's put some lengths in here too. We weren't given that in the problem, but we would be in a test, but here we don't. So let's say this is L, and let's say that the length here is L over 8 or something like that. So then we have, and let's say that we also don't know the force on of the bicep. Let's just, but it's what we're calling the max force, F max. So we do know we have F max. Okay, so the weight is going to be a clockwise torque, so that's minus mg times the lever arm L plus the F max times our lever arm of L over 8, and that's equal to 0. We have L. We can divide the whole thing by L. We can cancel out our L's, and then we could solve for our weight mg, and we would find that it is going to be equal to F max over 8, just F max over 8. What coefficient of static friction is required for the mountain goat to accelerate a 60-degree incline from rest to 3 meters per second during a 0.1 second interval? Okay, so let's draw this out. You've got some incline here, 60 degrees, I'll call that theta, and then we have our mountain goat, which is going to be accelerating up from 0 to 3 meters per second in 0.1 seconds. And so we're looking at we also have the word accelerate here. So I'm guessing that this is going to be an F equals ma thing. And we're thinking about accelerating up the incline, so let's draw our axes like this and put x over here, y here, and let's look at this in the x direction. So we're trying to figure out, to get an acceleration that's 0 to 3 in 0.1 seconds, what's the static friction force? So let's draw a free body diagram for the block, because I'm going to need that for the left hand side here. So we have our goat, which I'm drawing as a block, and then we have our mg down as always, normal force up, and then which direction is our static friction in? Well, the goat is wanting to accelerate up, but there's no upward forces here. And if we didn't have friction, which way would the goat slide? Well, it would slide down, right? So that means that the static friction force, which is, as we know, is mu equals, or times the normal force. That has to be upward. So let's now write out our forces in the x direction. So we have our static friction force, which is going in the positive x direction, minus some gravity. I'll let you work out that this is Fg sine theta. And then those are the only two forces in the x direction, so that's equal to m times acceleration in the x direction. But what is the acceleration in the x direction? Because we actually know it here. Well, it's 0 delta v over delta t, and so this, we know, is just going to be m times 3 meters per second, because it's going from 0 to 3, over the change in time, which is 0.1 seconds. So now all we'd have to do is we'd need to solve for the coefficient of static friction, but in order to do that we need to know that this is equal to mu s times the normal force, and keep in mind that our normal force is going to be equal to mg cosine theta. And so with this piece of information, and this equation here, should be able to solve for what the coefficient of static friction is. 21. A giraffe's head is about 3 meters above its heart. Blood reaches its head flowing through a small artery with a radius of 3 millimeters. Given that the viscosity of the blood is 4 times 10 to the minus third, what must be the minimum diastolic pressure produced by the giraffe's heart in order for the blood to flow to its head, where the pressure is 1 atmosphere? Okay, so as always, let's draw a picture of our giraffe. It's got a long neck here. It's got a head up there somewhere. We know up here the pressure is 1 atmosphere. We have a very narrow artery here, or not an artery, but an artery, that's 1 millimeter radius, and we're trying to figure out what the pressure is down here. So how would you do this? Well, we're looking for a change in pressure from a place down here to a place up here, and we also know that we're going to have viscosity involved. So okay, let's ask, what is actually causing the pressure to change going from the heart to up here at the head? Well, you know that if something's vertical, the gravity causes this pressure change. So you know that the change in pressure from, say, head to heart, or heart to head, let's just look at the magnitude of the pressure change, is going to be rho gh, and that means that this is a higher pressure down at the bottom. So the change we're looking at is higher pressure at the bottom, and then also we're going to have this plus some pressure change from it seems like there's viscosity in the problem. So when the blood flows up here, it's actually going to be the viscosity is going to make it hit the walls here, and the walls create a shear stress. And basically, we're going to have to use an equation for viscosity that we have to figure out what the pressure drop is from that this viscous fluid moving up this artery. So the one equation we have with viscosity and a pressure drop is Poiseuille, which is Q equals, what is it? Do you remember? Let's see. It's pi over 8, then the change in the pressure, viscosity, length of the tube, radius to the fourth, and then so we can rewrite this to get that delta P is equal to Q 8 viscosity length over pi r to the fourth, and I'll call this change in drop Poiseuille. So this is plus change in drop Poiseuille, and then so this is the pressure drop from the head to the heart. So if we calculate this, then we know that this is how much higher P is at the heart, but we know that at the head it's 1 atmosphere. So at the heart it's going to be this pressure change plus 1 atmosphere. So P equals 1 atmosphere plus rho GH plus change in pressure from Poiseuille. 22. A flea of 0.5 milligrams jumps 15 centimeters straight up into the air. During the jump, the flea accelerates from rest in about 1 millisecond. How much power does the flea produce? Okay, so what's the situation? We have a flea and it jumps up to a height of 0.15 meters, and so it has so there's actually two things going on, right? So it has a little time when it's like it jumps in 0.001 seconds, and then there's a second part where it flies up to this this height. So what do we want to calculate? We want to calculate the power, right? So this is the power during this part here. And if you look on your cheat sheet, hopefully you have work over change in time, and you know that the time is going to be 0.001 seconds. So now you just need to know the work. And the work is really the amount of energy that the flea is giving itself in this jump. And so to figure out the amount of energy, you can just figure out how much energy it has up here at the top, because that'll be the same as the kinetic energy it has down here at the bottom. So that'll just be the mass of the flea, which is 0.0005 grams, or 0.000000 kilograms, 5 kilograms, times g times the height, which is 0.15 meters, and then that will be the power. 23. You are running with a constant horizontal velocity of 10 meters per second. You jump up exerting a vertical force of 2.5 mg, that's mass times gravity, over a duration of 0.25 seconds. How far will you travel? I believe this is horizontally. It's talking about before you land. Okay, so as always, I'd like to draw a picture. So you start on the ground, you accelerate upward for 0.25 seconds from this force, which equals 2.5 mg. Why is it written, the force written like this, mg? Because it's similar to gravity, where gravity is usually just mg, and we know the acceleration is just g. This means that the acceleration upward is going to be equal to 2.5 g, right? I mean, I'm just using F equals ma, and we know that the force is equal to 2.5 mg, canceling out the m. So A equals 2.5 g. So that's our acceleration there. So that's the first little part. And then what will happen is we'll have some projectile motion because we're still moving at 10 meters per second to the right. And then we go and we land somewhere like here. And so we need to figure out how far we traveled in the horizontal direction. So we want to figure out what this L is. So usually when we have a problem like this, we want to calculate the change in time, because the change in time over the whole path is going to be the connection between the x and y directions, because it takes that one time to go up and then down, and also to go to the right. So if we can find the t it takes to go up and down, and then we can use it in our equations for the x motion. So okay, so let's first break this up. We have this first small piece which is called this delta t1 right there, and then this path, let's call the time it takes to do that delta t2. So delta t equals delta t1 plus delta t2, but we know delta t1 is just, we were told in the problem, 0.25 seconds. So all we need to find is delta t2 to find the time it takes to go along this path. So basically we're going from here to here, and if we focus on the y direction, what we can do is if we just focus on that, basically it's just like we're going up and then we're going down a little bit further, and so we want to be able to use the equation y as a function of time is equal to y naught plus v naught t plus 1/2 a t squared. And so to figure out y naught, well, we need to figure out how high we went when we were accelerating upward. To find v naught, we need to find the velocity we have when we get to here, get to this height, and then the acceleration in the y direction along this path is just going to be minus g. And then we can, if we know all of these, then we can solve for t. Oh, and we know that the y at the final time is going to be, so yf we know is going to be 0, because we're going to be landing on the ground here. Okay, so let's first focus on how to get y naught. So this height here is y naught, and so to get that we can use the same equation, but just for accelerating upward, where we have we're looking for the y final along this path. So here, let me star this path. So this is using this one for the starred path. So then y final is going to equal y initial, which is 0, plus the initial velocity before we accelerated, which is 0, plus 1/2 times at squared. Here the acceleration is an upward 2.5 g, and so that's going to be times the time, which we know is 0.25 seconds, and then so now we know that y final is going to be whatever this number is here. Actually, this is going to be, this is equal to y naught from up here. That's just equal to that there. So now how do we get v naught? Well, again, we know the acceleration from here to here, and we know how long we had that acceleration, so we can just use the equation that the acceleration
is equal to change in velocity over change in time, or that the change in velocity equals acceleration times change in time. We know that this is 2.5 g times 0.25 seconds. And so from that we know that this is equal to v naught. So now we have y naught and v naught. We also know g, and so we can use this equation. I'll rewrite the equation because we're going to solve it for when y is equal to 0. That's when we're here at the bottom. So basically we'll have 0 equals 1/2 2.5 g times 0.25 plus v naught, which is 0.25 seconds times 2.5 g. It's a lot of 2 and 5s going on here. And then that times our time, and then we have plus 1/2 a t squared, but our a is minus g, so here, let me just put that in there. This is a long one, sorry about this, guys, but you know, sometimes the problems are long. It's 1/2 g t squared, and then from this you can find t, like that, and then you can use that t in your horizontal equation. So then, or actually this, so from this you'll find delta t2. This is going to be delta t2 because that's the time to go from here down to here. So then you can use this delta t2, use delta t equals delta t1 plus delta t2, and then we can plug, now that we know this from is 0.25 seconds, and we know this one from here, we know delta t, and then we can use that x equals the velocity times the time, for this is for a constant velocity, and we know that the velocity is 10 meters per second, and we now know that t is this delta t we've calculated, and we can finally find the horizontal distance. 24. A cyclist in the Tour de France consumes 800 food calories per day. If he rides for 6 hours on level ground at a constant speed, how far can he travel in a day? Okay, doesn't seem like there's enough information here, probably. But what's the question asking? It's saying, okay, so we have this biker consuming this many calories, so he has a certain amount of energy, and he rides for 6 hours, I'm assuming, using up all of that energy by going at a constant speed. And we need to know how far. So we need to find a change in x. So how could we possibly figure out the change in x just from how much energy and time? Well, we have, okay, so we do have time. So if we know that we're looking for a distance and we have a time, then what we probably want to do is we'll probably want to use the equation that change in x is equal to the velocity times the change in time. And so we know the time. So now we just need to figure out what is the, so we know. So this is, what is v? Okay, well, if he's going at a constant speed and he's using up the calories, that means, you know, he's I'm thinking, like, you know, if you're going at a constant speed, you actually don't need to provide any force unless there's a force resisting your motion. So what I'm thinking is that if we draw a picture here of, this is going to be a horrible biker. So this biker, he's either has no force and is going at a constant speed, but since he's using up those calories, he's probably providing a forward force from the biker, and then there's resisting this force of drag back. And so if he's going at a constant speed, these two have to be equal, these forces, and we know that force from drag, which we know that's the magnitude of that's going to be equal to the force of the biker. So the force of drag is equal to 1/2 c, which is some coefficient that we're not given. So this is pressure drag because this isn't viscous. This is just, in air. So that's pressure drag times the cross-sectional area times the velocity squared. And so we know that now there's some force, but we want to find, we want to relate that force to this energies, the energy he's from eating these calories. So that means the connection between force and energy is work. And work is equal to force times distance. Or another equation we could think of is power is equal to work over change in time, which is equal force times velocity. And so we know that this force is going to be the force from the biker. The velocity is what we're looking for. And then we could set, and then on this side we know that our time is 6 hours, and we know this from this work from 8,000 calories, food calories. So from this equation we could find our velocity if we knew, c, and we knew the cross-sectional, we knew this c, we knew this cross-sectional area a, we knew the density of air, and then we could find our velocity, and then we could plug that into this equation up here, and we could find out what the distance was.